Previously in the semester, we had talked about the different types of inferences. And just for a reminder, an inference is when you take information from a sample and you infer your calculations upon the population. So one type of inference that we discussed was Chapter 7, which dealt with estimation. We did not know a population value, so we estimated it by using a sample and then inferring our information onto the population. Well, another type of inference is hypothesis testing. So hypothesis testing is another type of inference. So let's take a look at what hypothesis testing involves. First off, the purpose of a hypothesis test. The purpose is to verify the validity of a claim about a population based on a single sample. So it's to verify the validity of a claim. That'll make more sense as we dive into this. Now, for all of these problems, we're going to follow a 5-step sequence. Okay, so we're going to follow 5 steps. We're going to first state our hypotheses. Then we're going to calculate a test statistic, find the probability, then we're going to make a decision, which means reject or fail to reject, and then we will write our conclusion. Now, here's what is going on in a hypothesis test. You are given a population, but you think it is different. Okay, well, what if I told you the population average age of NOC students is 39 years old. So you're given a population mean. We're saying that for all NOC students that the population average age is 39 years old. But you look at that and you go, you know what? I think it's different than that. I don't think it's 39 years old. So what we'll do is we'll take a sample of the population and find its sample mean, which is X bar. If the sample mean is far enough away from the given population mean, then you can reject this claim and conclude that it is changed. So that's what we're looking to do. So let's take each step at a time. So here is step 1, which is stating the hypotheses. Now, there are 2 hypotheses. The first hypothesis is what is called the null hypothesis, believed to be true unless there is overwhelming evidence to the contrary. So the null hypothesis is written with using this symbol H sub 0, mu is equal to a number. So if I was going to create the null hypothesis based upon this example up here, I would write the null hypothesis is mu is equal to 39. So that's what the null hypothesis would look like. This is the statement under investigation. So this is what, in essence, if you want to say, what we're putting on trial to see if it's changed or not. This is the top population mean that is still true, used to be true, may be true. This will be given to you in the problem. However, you think it is different or is changed. You look at this and say, well, maybe it used to be that, but I don't think it is. So then what we do is we state what is called our alternate hypothesis. And the alternate hypothesis is known as the research hypothesis because it states the position a researcher is attempting to establish. This is what the researcher, the alternate hypothesis, thinks it has changed to. So that we use H sub 1, and it is a statement of inequality. It will either be less than, smaller than, greater than, more than, not equal to, different from. That's how that wording would be. So this is the statement you will adopt when the evidence is so strong that you reject this. So if we have enough evidence to say this isn't true, then the alternate is what we would say is true now. Now my guess is, it could be any of these inequalities, but my guess is we would think that the average age of NOC students is less than 39. So if we have enough evidence, we can say this is not true, this is true. We either think the population mean is smaller, which would be less than, larger would be greater than, or just different, which would be not equal to. This is determined in the question part of the problem. So let's do a quick example of just looking at how to set up the null and the alternate hypothesis. It has been recorded that the average weight of all 20-year-old women is 128 pounds. So the average weight is 128 pounds. So if you want to set up a statistical test to challenge the claim of 128 pounds, what would you use for the null hypothesis? So the null is h sub 0, and it's always mu is equal to some number. Well, that was given to me. It said that the average was 128 pounds, so that would be my null hypothesis. But suppose you wanted to test the claim that the average weight for 20-year-old women is heavier. What would you use for the alternate? So, alternate is h sub 1. And it's going to be mu, and you're still going to use 128. That number doesn't change, but you think it's less than, greater than, or not equal to. Well, heavier would represent a greater than inequality. Because of the popularity of CrossFit, you believe the average weight of 20-year-old women is below 128 pounds. What would you use for the alternate hypothesis? Well, if this is the claim I was testing, then I would say mu is below would be less than 128 pounds. So here would be my null, and just depending upon which you thought it had changed to, you would use greater than or less than. These are just some examples. Now, the alternate hypothesis tells us what type of tests that we have. So the types of statistical test is determined by the alternate hypothesis. So the alternate hypothesis represents the claim that is being made and tested. Therefore, the alternate hypothesis determines the type of test that you are going to do. So, if you'll notice here, when the alternate is a less than statement, that tells me I have a left-tailed test. So a left-tailed test would look like this. If my alternate is a greater than, then we have a right-tailed test. Which would look like this. And then, if your alternate is the inequality not equal to, we have a two-tailed test. Which would look like this. Now, eventually in our test, we're going to look for this area shaded in the curve. This goes back to finding the probability off of the Z table. Well, when it's less than, we just go to the table and use that number. When it's greater than, we do 1 minus the number from the table. When it is not equal to, this one is different. Previously, we had done shading in between, but now the shading is the two tails. So we'll actually do an example like this that I'll show you how to handle that one. All right, moving on. All right, so that gets us set up. And now what we're going to do is actually look at all 5 steps. So we have hypothesis tests when sigma is given. And if you recall from before, when sigma is given, what that dictates is we use the z-table. Now, we've already discussed step 1. That's setting up your hypotheses. So that's what we've just discussed. So now we're going to look at step 2, and step 2 is the calculation of our test statistic. And that is your z value. And remember, the z value tells you how many standard deviations away from the mean that you are. If you are far enough away from the mean, we will reject the null or say it is incorrect and conclude the alternate. Step 3 is going to be when we find the probability. Now this is based upon what type of a test that you have. Now we've already talked about the different types of tests that we can have. So, let me move this over just a little bit. When the alternate is a less than, we have a left-tailed test. Step 2 would give us this test statistic. It would tell us what this z value is. So to find the probability, the p-value will be the probability that z is less than whatever number we calculated. And because it's shaded to the left, that's why it's less than. So we will look this up in the standard normal table, just like in chapter 6, and since it is less than, you just use the number from the table. Then we have the right-tailed test. This is when the alternate hypothesis is greater than. Step 2 would be calculating this test statistic. So to find the p-value, you're going to take the probability that z is greater than the test statistic, which means look up the test statistic in the standard normal table. Since this is area to the right, you will take 1 minus the number from the table. Now, the one that is different that I already previously spoke of is the two-tailed test. And this is when the alternate hypothesis is not equal to. Now, in step 2, you will calculate a z value. If that z value is positive, then it's this test statistic, which means this one is just its opposite. So in step 2, if you would have calculated 1.25, then this one is negative 1.25 because this is symmetrical. In step 2, had you calculated negative 2.75, then this one is positive 2.75. So what you will do to find the p-value is you'll take the probability that z is less than the negative test statistic, which would give you this area, and add it to the probability that z is greater than the positive test statistic, which would give you this area. So as you look up these probabilities in the standard normal table, you will find that they are the same. So this area and this area is going to be the same amount, which makes sense because it's symmetrical. This makes sense since the standard normal curve is symmetrical. Because of this, I usually just look up the negative test statistic and multiply the table value by 2. So again, we'll do an example of this so you'll get to see it actually completed. But before we do, there's one last thing we need to talk about when you're doing hypothesis testing, and that is what is called the level of significance. The level of significance is a Greek symbol which looks like a little fish, and it's called alpha. Alpha represents the probability that our conclusion, so we did a test, but we got the wrong results. So we made the decision to say or reject the null when it is actually a true statement. This is what is known as a type 1 error. Alpha will either be 1% or it will be written as 0.01 or it will be 5% or written as 0.05. That will always be given in the problem. So alpha is telling us how often we are willing to make a type 1 error. So when I'm doing a test, there's always a chance of an error being made. Am I only willing for a mistake being made 1% of the time or 5% of the time? Again, you're not going to have to make that decision. It will be done for you. The p-value, now the p-value is what we calculate in step 3. That's when we use the table. This p-value is telling us the probability that we will make a type 1 error. So as long as the p-value, how often an error will be made, is smaller or less than alpha, we will have enough evidence to make our case. Our sample mean was so far away from the population mean that we can conclude that the population mean has changed. So when we make that comparison, it leads us to step 4, which is when we make our decision. Now, just for purposes of try to help explain this, I'm going to rewrite that example that I did with our null and our alternate. Now, if our p-value, which was calculated in step 3, is less than or equal to alpha, then we would reject the null. So if the p-value is less than alpha, we would reject that the average age of NOC students is 39, and we would conclude that it is actually less than 39. If the p-value in step 3 is greater than alpha, then we fail to reject the null, which basically just means we have not proven anything. We've not proven that the average age is 39. We've just not shown that it's less than 39. And then lastly is step 5, which is your conclusion. If in step 4 you reject, then you have sufficient evidence to say it's changed to the alternate. If you fail to reject, then you don't have enough evidence or you have insufficient evidence to conclude that it's changed to the alternate. All right, so at this point you may be on overload. So let's go ahead and do some problems. I think once you see an example worked out each step, it hopefully won't seem quite so overwhelming. All right, here we have an example. A company claims its laptop batteries average more than 3.5 hours of use per charge. A sample of 45 laptop batteries lasted an average of 3.72 hours. Assume the population standard deviation is 0.7 hours. Test the company's claim using a significance level of 0.05. Okay, the hypotheses. So we know in the hypotheses that we're going to have the null, which will be mu is equal to some number, and the alternate, which is going to be mu is less than, greater than, or not equal. So I have to come up here and try to figure out what those values are. Well, if you look at the first sentence, a company claims its laptop batteries average more than 3.5 hours of use per charge. So more than, the alternate would be greater than 3.5. So the null would be that it's equal to 3.5. So we're testing the claim to see if we can reject the null and say it is greater than 3.5. Now, at this point, it's a good idea to remember that the alternate is what dictates what type of test that we have. So since it is greater than, we know we have a right-tailed test. So that's step 1. Now, in step 2, we're going to calculate the test statistic. So I've got to write down all the information given. A sample of 45, so I know N equals 45. And this sample of 45 lasted an average of 3.72. So this is a sample, so this average is X bar. Assume the population standard deviation sigma is 0.7. Test the company's claim using a level significance of 0.05. Okay, well now I have all the information to calculate my test statistic. Since the population standard deviation is known, then that tells me I am going to calculate a z-value. And that z-value is X bar 3.72 minus mu of 3.5 divided by sigma 0.7 divided by the square root of N, which is 45. So I put that into my calculator. Let's see if I can do this as a fraction. So in the numerator, I don't even need that. So 3.72 minus 3.5. And the denominator is also a fraction. Yep, it's going to let me 0.7. And then this is the square root of 45. Come out from under, come all the way out and hit enter. And I get 2.108, and it's a z-value, so I'm going to round to 2 decimal places, 2.11. Now, if you have a calculator that doesn't do in fraction form, like this calculator, then just do open parentheses, 3.72 minus 3.5, close parentheses, divided by open parentheses, 0.7, divided by the square root of, and this opens parentheses for the radical, so I'll put in 45, close the radical, close the denominator, and I get the same answer. That's why the multi-view is so nice. So what we have found is that this is 2.11 standard deviations away. So if you remember, here is your mu, and we're saying we're 2 full standard deviations and 0.11 from that away. So now, in step 3, I'm going to calculate the p-value. Well, the p-value, since the alternate is a greater than, we say the p-value is the probability that z, and because the alternate is greater than, then we say greater than the test statistic 2.11, and because it's greater than, I know I do 1 minus the number from the table. So now I'm going to go to the table and find whoops, that's the negative one. 2.11 is 0.9826. Which is 0.0174. So this is your p-value. All right, now, the p-value is going to help me make my decision because in step 4, we're going to compare the p-value, and the p-value is 0.0174. Now I'm going to go ahead and convert that into a percentages because for some students it's easier to compare numbers when they're as a percentage. And we're going to compare that to alpha. And alpha was given as 0.05, and when I convert that, that would be the percentage 5%. So here's the probability that we make a type 1 error. Here's the probability we're willing to make a type 1 error. So since this is less than, that tells me then I reject the null hypothesis, which means when we reject it, we're saying the null is incorrect. We have shown in our test or concluded that it has changed to the alternate. So when we reject, that tells me there is sufficient evidence to conclude the average laptop battery charge is more than 3.5 hours. Now, let me point a few things out. Because we rejected, what reject tells me is I reject the null and I conclude the alternate. So I have sufficient evidence to conclude that it is changed to the alternate. So my conclusion, the keys are sufficient evidence, and then the information that follows is just basically explaining the alternate. We have sufficient evidence to conclude the average laptop battery charge is more than 3.5 hours. So that's how that conclusion is written. All right. Doing another. Going to do two more examples of this. Recent data shows that the average adult consumes 1.7 cups of coffee per day. Assume the population standard deviation is 0.5 cups per day. A sample of 30 adults averaged 1.85 cups of coffee per day. Test a researcher's claim that the actual amount of coffee consumed by the average adult is different from 1.7 cups per day. Use alpha at 0.05 for your significance level. Okay, so step one is our hypotheses, which we know is the null, mu is equal to some number, and the alternate, and that will be an inequality. So I've got to come up here and see what the population average is, and then if I think it's less than, greater than, or not equal to. So to find the number, it says recent data shows that the average adult consumes 1.7 cups. So this would be 1.7. And as I read the remainder, I come down here and it says test a researcher's claim that the actual amount of coffee consumed by the average adult is different from 1.7 cups. Different from means is not equal to. It could be less than, it could be greater than. I don't care. I'm just saying it's different from. And these numbers are always the same. Now, a reminder, the alternate is what tells us what type of test that we have. So the alternate is telling me that I have a two-tailed test. Now, it's this two-tailed one that is different on how we find the probability, because it's the tails rather than what's inside. So this is an example I told you we would eventually do. Okay, step two is your test statistic. And I've got to figure out what type of value I'm calculating. So I'm going to write the rest of my information. We've got the 1.7, so it says assume the population standard deviation. So I know that sigma is 0.5. A sample of 30 adults, n equals 30, and those 30 adults averaged 1.85. So that's x bar. So there's the additional information. Now, because the population standard deviation is known, we know that we're calculating a z-value. And it is x bar, 1.85, minus mu, 1.7, divided by sigma, 0.5, divided by the square root of n, 30. So putting this into your calculator, Whoops, I keep getting an error. So let me do it up here. I was going to try, I have it calculated and I was just going to confirm, but I'm going to go ahead and do it. 1.85 minus 1.7. Denominator is another fraction of 0.5 square root of 30, 1.64. Now, because we have a two-tailed test, I only calculate one test statistic. But because this is symmetrical, I know that this is 1.64. And because it's symmetrical, then I know this is negative 1.64. Because this area shaded and this area shaded is the exact same amount. And that's important for step 3. So for step 3, we first have to find the area of this, which is a less than. So that would be the probability that z is less than negative 1.64. And we're going to add that to finding the area of this, which is the probability that z is greater than positive 1.64. So let's go to our table. This is a less than, so I just look up negative 1.64 on my table and use that number. Negative 1.64 is 0.0505. And I'm going to add that. Now this is a greater than. So typically with a greater than, what we do is 1 minus the number from the table. So I'm going to look up positive 1.64, which is 0.9495. Now this is what I was stating earlier. Since this is symmetrical, when you take 1 minus 0.9495, you're going to notice that you get the exact same on both sides. So both tails are 0.0505, which is 0.101. So this is my p-value. Now, when you're doing a two-tail, if you want, you can just find this one and double it. That would give you this correct answer as well. All right, so now in step 4, which is when we make our decision, this was finding the p-value. We are going to compare the p-value 0.101, which as a percentage would be 10.1%, to alpha, which is 0.05. That was given up in the original problem, which is 5%. So the likelihood that we make a type 1 error is greater than our willingness to make a type 1 error. So I'm not willing to go on record and say things have changed. So in this case, we fail to reject the null, which which basically what we're saying is we've proved nothing. The last example, we rejected this and said I can claim this, but now since we failed to reject, I can't reject this claim, which means I cannot embrace that it has changed to the alternate. So now there is insufficient evidence to conclude the average cups of coffee consumed by adults is different than 1.7 cups. Now, again, how I write my conclusion is all based upon the hypotheses. So, because we failed to reject, there is insufficient evidence to conclude. So we are saying there's not enough evidence to conclude it is changed to the alternate. So that's why the rest of my sentence refers back to the alternate. The average cups of coffee consumed by adults is different than 1.7. Basically, we're saying we don't have enough evidence to prove that. Okay, one last example, and then hopefully you are getting a hang of this. A large furniture store has begun a new campaign on local television. Before the campaign, the long-term average daily sales were, so I see this, that's going to help me set up my hypotheses. A random sample of 40 days during the new ad campaign gave a sample mean daily sale average of 23,910. Does this indicate that the population mean daily sales are now more than the 24,819? Use 1% level of significance and assume that sigma is 2,117. Okay, what I've underlined is what is going to help me set up my hypotheses. So my null is that mu is equal to 24,819. My alternate is that mu is more than or greater than 24,819. Okay, so because my alternate is a greater than, I have a right-tailed test. Now, we've done right-tailed before. We've not done a left-tailed. I think I meant to change this to a left-tailed, but we're going to go with it. But I'll make a statement when we get to the p-value. Okay, so now we're going to go to step 2, which is our test statistic. And we know that mu is 24,819. So we had a random sample of 40 days. So n equals 40. And that 40 had an average, or x bar, of 23,910. And it tells me that sigma is 2,017. And because I have because I have the population standard deviation, then I know I am calculating a z-value. So it would be x bar minus mu divided by sigma divided by the square root of n. So 23,910 minus 24,819, 2017, the square root of 40, negative 2.85. Oh, you know what? I have to change that. I changed my numbers. I'm so sorry. Okay. We're doing an oops, and for that I apologize. This needs to read, I changed my numbers for less than, so I need to just make that change, okay? So make this less than, okay? So here, I'm going to do this on a different piece of paper. Again, I am so sorry, but we're just going to go with it. This is called being flexible. So I changed the numbers for less than, but I forgot to change the wording of more than to less than, so it kind of messes this up. So this is going to be the null is mu is equal to 24,819, and the alternate is less than 24,819. Okay, so this needs to be a less than, so now my numbers make sense. Originally, this problem was a greater than, but I adjusted this number, so I wanted a less than. I just neglected to change that wording. So this is the correct step 1. So in step 2, this test statistic, so I'm just going to do a little adjustment. Again, I apologize, but I do not want to record this all over again. So that's why we're going. So we're just going to change this. All right, so that's the correct hypotheses. So here's step 2, which we calculated to be negative 2.85. So that tells me that this z is equal to negative 2.85. So that's what it would look like. So step 3, my p-value is the probability that z, and since the alternate is less than, this has to be less than, my test statistic that I calculated, negative 2.85, and because it's a less than, all I have to do is use the number from the table. So when I use the number from the table, negative 2.85, it's 0.0022. So here's my p-value. So then in step 4, for our decision, we're going to compare the p-value. And again, I'm going to convert that to a percentage, which is 0.22%, less than 1%. And we're going to compare that to alpha, which this problem said to use 1%. Well, this is less than 1%, so less than. So we reject the null, and rejecting the null means we're going to reject the claim that it's equal to, and now we can conclude that it is less than. So basically we've proven our case. So there is sufficient evidence to conclude the average daily sales are less than $24,819. And again, because we rejected, there was sufficient evidence. That concludes 8.1.